Welcome everyone. I'm Norman Wildberger, and today we're going to be talking about addition. Obviously one of the fundamental skills that all students, young students in primary school have to learn. So we're going to be talking about relatively simple aspects of addition that kindergarten, year one students are going to be learning. There's going to be some memorization required for those students. But we want to organize the approach so that the memorization is as systematic as possible. We're going to also run into an interesting issue relating to the names of numbers once we get past the numbers up to 10. So here's a very primitive example of addition. We have this number plus this number equals this number. This is our primitive kindergarten approach to numbers, simply as rectangles or strings of squares. And the way we add them is geometrically very simple. We just concatenate the two strings together, push the two rectangles up together so that they form one. So in the Roman system, these two numbers are represented by these strings of ones. 1, 1, 1, 1 for that one. 1, 1, 1, 1, 1 for that one. And adding them just amounts to putting those two strings together to get 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so then we ended up giving names to these numbers. So this is really the number 4, this is the number 5, this is the number 9. And here's our Hindu Arabic symbols for those. So we would today write 4 plus 5 equals 9. Okay. So that's one example of the many facts that young people have to learn. They have to memorize that so that it's second nature, so that they don't even think about it. You ask them what 4 plus 5 is, immediately they say 9. Okay, in my opinion, there are sort of 3 stages of learning addition, of becoming familiar with the operation. The first stage is the issue of adding two numbers which are in the range 1 to 5. Like here. These numbers are both in the range 1 to 5. This is a particularly simple kind of addition. I think it's good for learners to start with numbers in that range. And then the next step, which is really a step up, is to add two numbers in the range 1 to 10. It turns out that's quite considerably more sophisticated. So students should start with addition in the range 1 to 5 and then move up to addition in the range 1 to 10. And then only after that, the third stage is moving towards adding any two numbers. In this lecture today, we're going to be just talking about these first two stages of addition. So let's start with stage 1. Adding two numbers in the range 1 to 5. So we want to do this in a systematic way. And so it makes sense to start with the case when we're adding 1 to a number. For example, 1 plus 1, or 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. It's not too hard to work out what these things are, of course. 1 plus 1, we just bring the squares together, we get 2. 1 plus 2, bring the squares together, we get 3. 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6. And they are the corresponding Hindu Arabic equation representing the same thing. And pretty obviously, adding 1 is very simple because it just gives us the next number. If we add 1 to 4, we're getting the next number after 4, namely 5. Now there's a similar kind of opposite version of the same equations where we add the two numbers in a different order, where we add 1 after the number rather than before. So 2 plus 1, of course it's still 3. 3 plus 1 is still 4. 4 plus 1 is still 5. 5 plus 1 is 6. And there are the expressions in Hindu Arabic form. And pretty clearly, if we add 1 plus 2, this combination, we're getting the same thing as when we add 2 plus 1. It doesn't matter which order we're taking these two strings in. We have these two rectangles. We can either do this one together with this one, or we can interchange in this order. The number of squares in the result is going to be the same. And that's the commutative law of addition. And here's our sort of fancy expression for that. M plus n equals n plus m. That's our way of saying that no matter what numbers we choose, m and n, doesn't matter if we add m plus n, we get the same thing as n plus m. All right, so those are probably the simplest kinds of addition, adding 1 to a number. After that, we get to add 2 to a number. So let's consider adding 2 to a number. For example, 2 plus 4 equals 6. 2 plus 4 equals 6. If we didn't already know that, we could think about that in 2 steps. We could think, first of all, of rewriting 2 plus 4 as 1 plus 1 plus 4, breaking up the 2 into 1 plus 1. And then we could put these together by first combining this 1 with that 4, which we assume we already know what that is. That's from the previous slide, the next number past 4, namely 5. And then at the next stage, we have to do exactly the same. We have to add 1 to that, so we're getting the next number past 5, which is 6. So we can also say what we're doing here, we're thinking about it. 2 plus 4 is 1 plus 1 plus 4, and that's the same as 1 plus 5, and that's 6. So in other words, if we know how to add 1 to a number, then we know how to add 2 to a number. We just add 1 and then add 1 again. So we add 1 twice. And here's the other way around, where we add 2 after the number rather than before. So 4 plus 2 is the same as 4 plus 1 plus 1. And we can think of that as being 5 plus 1. And that gives us then 6. And a little thought shows that another way of saying what's happening here is that adding 2 gives us the number after the next one. So if we add 2 to 4, we're not getting 5, but we're getting the one after that, namely 6. If we add 2 to 3, we don't get 4, we get rather 5. If we add 2 to 7, we go to 9, etc. So first we learn how to add 1. Then we add 2, then we extend to adding 3, 4, and 5. So let's organize all the additions involving the numbers 1 through 5 in a table, which makes it somewhat easier to see the pattern. In this table I have all the additions involving the numbers 1 through 5. 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6. And here's adding 2. 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7. In either case, for example, we get the number that's 2 past 4. 3 plus 1 is 4. 3 plus 2 is 5, 3 plus 3 is 6, 3 plus 4 is 7, 3 plus 5 is 8. 4 plus 1 is 5, 4 plus 2 equals 6, 4 plus 3 equals 7, 4 plus 4 equals 8, 4 plus 5 equals 9. And 5 plus 1 equals 6, 5 plus 2 equals 7, 5 plus 3 equals 8, 5 plus 4 equals 9, and 5 plus 5 equals 10. This is a table which is like a rectangle. In fact, it's a 5 by 5 table. It's got 5 rows and it has 5 columns. And it's kind of a pleasant table. There's an obvious pattern. If we look at the answers, here we get an answer of 2. Here and here we get an answer of 3. Along here we get an answer of 4s. Along this sort of diagonal we get answer of 5. Then along this diagonal we get 6s. And then along here we get 7s. Here 8, here 9, and here 10. It's also important to remark that there's some symmetry in this table, which makes it, in fact, less difficult to memorize than it might appear, because once you've figured out what 2 plus 4 is, then 4 plus 2 is the same. So there's a symmetry between this entry and this entry, or between this entry and this entry, or this entry and this entry. Sort of a mirror image along this main diagonal. So in some sense we could say that what we really only need to remember is everything on that diagonal and say above it, or everything on that diagonal and below it. The commutative law takes care of the other ones. Now it's a fact that young people have to learn this table one way or the other. And I'm not going to make definitive statements about how young people should learn these things. I think that's best left to primary school educators to figure out. I'm just pointing out that this is a very important preliminary understanding that all students of mathematics have to make progress in arithmetic and consequently in mathematics. Let's rewrite this table in a little bit, I think, more attractive way. There's a little bit too much in this table, and it's possible to make it more efficient and therefore perhaps easier to remember. So here's this more efficient pared down version of this addition table. Here it is right here. So let's have a good look at this, make sure we understand what this is telling us. First of all, this is a table for addition. So this little sign that I'm putting here makes it clear that we're talking about addition, not multiplication. Later on, we'll have a similar kind of table for multiplication, which will be a little bit more complicated. This is a pretty simple table, as you can see, because the pattern is reasonably clear. What is involved here? Well, we have some lines here separating numbers 1, 2, 3, 4, 5 along here, and numbers 1, 2, 3, 4, 5 along here with the main body of the table. And the way we read this is, if we want to add two numbers, let's say 3 and 4, we go down this first column till we get to the first number 3. We go along this top row till we get to the second number 4. So we're adding 3 plus 4. We'd like to know what that is. Then we go along this row and down this column to where they meet. And the entry here is the answer of what is 3 plus 4. So 3 plus 4 is 7. Let's do some more. 4 plus 2 is 6. 5 plus 3 is 8. 3 plus 5 would be 3 plus 5. That's also 8. So the symmetry that we talked about before, the commutative law symmetry, is telling us that this table is symmetric if we reflect along this diagonal. This 7 is the same as that. That 5 is the same as that. That 6 is the same as that. 7 is the same as that. And that 9 is the same as that. Of course, it's pretty easy to see here that there's a nice pattern because along every row, we're just going up one at a time. Down every column, we're just going up one at a time. And along these sort of cross diagonals, we have 3s, 4s, 5s, 6, 7, 8, 9, 10. So if you forgot this table, it wouldn't be too hard by starting out with 1 plus 1 is 2 to reasonably quickly draw the rest of the table. Okay, it's not a mystery of how to construct this table. 1 plus 1 is 2, that's the first or the most simplest addition, and everything else is built up from that by moving sequentially one up as we go along the row or the column. Okay, so students of course have to learn this, and they have to find some way of putting that in their long-term memory. And that's a very important job for teachers and for parents. And you might use cue cards, and you might use lots of examples, you might use your hands. And I'd like to point out the usefulness of thinking about our hands as a way of encoding or perhaps allowing us to calculate such simple sums, or especially for young people, without if they've forgotten it. So here are my hands, and left hand and right hand, that's what's represented here. And we can use our hands, or the fingers on our hands, to do some counting. And there's different ways of doing this. Different cultures have different ways of representing the various numbers. Probably, I think it's simplest if we say use the left hand, the index finger to be number 1, and then that combination is 2, and that combination is 3, and that combination is 4, and then when we add the thumb, we get 5. And on the other hand, too, we'll represent this to be 1, this is 2, this is 3, this is 4, and this is 5. So we're only dealing with the numbers from 1 to 5 at this stage. So for example, if a student wanted to use his hands to calculate 3 plus 4, what they could do is they could use this hand for the first number, 3, this hand for the second number, 4, and then they could use their fingers. And how would that work? Well, the number 3 represented on this hand would be that. The number 4 represented in this hand would be that. So there's 3 and there's 4. And the student can think about adding them is just putting them together. Well, then you have to count. How many is that? 1, 2, 3, 4, 5, 6, 7. So 3 plus 4 is 7. This represents the final counting. After you put them together, the student can count them off one by one till they get to 7. A variant on that would be to say, all right, we'll start with 3 and then we'll add 4. So adding that 4 means we get 4 and then 5 and then 6 and then 7. In other words, we can assume that we already know we have 3 because that's the first number, and then we're adding one more to get 4, another one more to get 5, and then one more to get 6, and then a fourth one more to get 7. So it's quite natural. Of course, this is where our number system arose, by fingers of the hands, and it's quite reasonable for students to do this. But at some point they have to go beyond that, and they have to let go of the hands and think symbolically. So ultimately, when a student sees 3 plus 4, they should be able to say 7 without, in their minds or under their desk, using their fingers. Okay. So this is a preliminary kind of business, but later on we just want to memorize this table and have it solidly in there so that they can very, very quickly tell us the result of the sum of any two numbers. 4 plus 5, it's 9. Very quick. Probably it's not bad even just repetition. If a student has to read this table, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6. If you read that table simply, do that a couple of times a day, probably it doesn't take too many weeks before those facts are solidified into the long-term memory. So all the numbers involved in this 5 by 5 addition table are all in the range of our basic first 10 numbers, from 1 to 10. And as the student becomes familiar with addition, they should also become more and more familiar with these 10 numbers and their relative positions. So by relative position, I mean that given any number, they should know which is the next number. They should know which is the previous number. It should not be too hard for them to figure out what's the number that's after the next number, or what's the number that's before the previous number. So of course, moving to the right in this list increases by 1, or if you like, adds 1. Going from here to here is adding 1. From here to here is adding 1. While moving to the left decreases by 1. Well, that's subtraction, which we haven't talked about, but it's subtracting 1, it's taking 1 away. So here's our addition table again, and I've just pointed out this cross diagonal here, various 7s, which are the result of 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2. Those are all the ways of getting 7 by adding two numbers. And it's useful for students to be aware that if you have two numbers and you know what the answer is, that if you decrease or increase one of the numbers and simultaneously decrease the other, then the result is the same. So if you know what 2 plus 5 is, it's 7, then if you increase the 2 by 1 and simultaneously you decrease the 5 by 1, then you get 3 plus 4, that's also got to be 7. So it's a way of helping organize our understanding of the addition table. So for example, let's have a look at 2 plus 3. There's 2 plus 3 is 5. If I happen to increase one of the two numbers, suppose I increase the 2 to 3. So instead of having 2 plus 3, I have 3 plus 3. So I've increased that number by 1, then the result is also increased by 1. Or if I increase the 3 by 1, then I also increase the answer by 1. So if 2 plus 3 is 5, then 2 plus 4 is 6. So students should get a sense of the interconnectedness of this table, that adjacent entries have a direct and easy to understand relation to the entry that you've started with. If you move one of these numbers up, then the answer moves up by the same corresponding amount. If you move one of these numbers up, or perhaps down, then the answer moves up or down a corresponding amount. So it's good that students get a really varied understanding of this, that they explore this with many different examples and many different problems that can illustrate various aspects of this. Okay? It's the solid, basic understanding that underlies addition. Numbers from 1 to 5. So now let's move to stage 2 of addition, where we extend the range that we're considering to numbers between 1 and 10. So how do we add two numbers between 1 and 10? And how do we teach young people about that? Well, this is the kind of situation we're talking about. We have two numbers, perhaps like this one and this one. This one's 6, this is 7. When we add them, we get this number here. And I remind you that the idea to simplify our expression for such a longish number is to peel off a 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And represent that 10, say, by that one red square. And then there will be 3 left over. So we end up with 10 as well as 3. In the simplified Roman system, this would be represented by having 6 there, 7 there, and there is our 10, 3. And of course, in Hindu-Arabic system, we would usually say this is 6 plus 7 equals 13. 13 is the usual number for this Roman expression. Of course, now we must extend the range of the numbers that we're considering from not just 1 to 10, but 1 up to, in fact, 20, because those are the possibilities that we can get if we take two numbers in this range and add them. So a preliminary to this kind of addition is to have consistent names for the numbers bigger than 10, or say between 10 and 20. And now we come to an interesting but somewhat delicate issue. That is having to do with the names for numbers. We have our symbols for numbers, the Hindu-Arabic symbols. But so far we only have names for essentially the first 10 of them. What about the names for higher numbers, say the ones between 10 and up to 20? Unfortunately, our names for these numbers, and in fact our naming system in general, is rather haphazard and illogical in many places. This is a problem with the English names for numbers and doesn't necessarily extend to other languages. Other languages also have problems, but some languages deal with this challenge much more efficiently and effectively. And that means that students in these other languages, and I'm thinking of Asian languages here, they have a great advantage when it comes to learning arithmetic. I think this point is not perhaps properly understood and properly acknowledged by educators. To a certain extent, there's nothing it seems that we can do about it, because the names for our numbers are so entrenched in our system. Nevertheless, if there is a weakness, it is good to acknowledge it, even if we are not currently in a position to overcome it. So our names for these numbers in English are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's not a bad naming system. It's not particularly good, but I don't think it's particularly bad. There's clearly something arbitrary about those names. The main thing that we want these names to have is that they be recognizably distinct, so that there's little possible confusion between one and the other. And the other thing that we would like them to be is to be relatively short. One syllable if possible. Now these are all one-syllable words with the exception of 7, which unfortunately is a two-syllable word, and it does introduce a little bit of additional time required to express numbers that involve 7. Unfortunately, the problems with our naming are much greater when we look at these range of numbers. The numbers that we usually call 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, if you're any person over the age of 10 in the English-speaking world, you will know these words and you will be very familiar with them. However, if you're a very young person, it takes some time to learn these words, and it's not particularly logical, the pattern of the names that we're using. The words are rather long, and their connections with the symbols are a little bit arbitrary, somewhat tenuous. Okay, we can recognize the 12 sounds like a 2, the 13 sounds like a 3, there's a 4 and 14, there's almost a 5 in there, but it's spelled differently, although sometimes it's still spelled F-I-V-E-T-E-E-N. There's a 6 obviously there, a 7 there, that we see an 8 there, a 9 there, a 20, that seems to come out of the blue. As for the 10s, well, the 10 is sort of represented by this elongated 10, which is now a teen for some strange reason, and that only starts with 13, and 12 and 11 are somewhat odd. Now, the adults among us are so used to this, we don't bat an eye. We say, well, that's just the way life is. Well, here is a proposed alternate system. This is another way that we might think about naming these numbers. And it has a lot to recommend it, this alternate way. So we, logically, looking at this is 110 and 11, which is encoded very efficiently by the two words 10, 1, reading left to right. Here is 10 and 2, so a good name for this number would be 10, 2. Then here is 10, 3, here is 10, 4, and the pattern is completely obvious. 10, 5, 10, 6, 10, 7, 10, 8, 10, 9, until this number. What do we see here? We see 2 10s and 0 1s, so we don't need to include the 1s, we just say 210. So am I seriously proposing that we change from this traditional naming system to this much more logical, sensible one? Well, not altogether. But I am proposing it in a small way. I'm suggesting that you think about it. You think about the possible advantages in having a naming system that's like this. It would make the job of learning arithmetic for young people much simpler. And the idea that mathematics is a logical enterprise, that it's not dependent on a lot of ad hoc things that you have to memorize. It instills that idea more firmly into young people's minds and gives them confidence that they can understand patterns and learn patterns and trust them. I think the education of young people in Western countries in the current time would be vastly improved if somehow we could miraculously take our magic wand and replace usage of these names with usage of these names. So I wanted to point that out. Maybe people can give some thought to this suggestion. And just for fun, I might actually try to use these new simplified names instead of these ones. You'll easily, of course, be able to translate, but just to get you used to thinking about this as an alternative possibility. So here then is the full addition table for numbers in the range 1 to 10. It's a lot like our earlier addition table, which in fact is just here in the top left-hand corner. That's exactly a repetition of what we were talking about before. But now we're extending it so that the numbers go not from 1 to 5, but up till 10 in both directions. So for example, if we want to know what is 6 plus 7, we go down here, down the first column to the 6, across this first row to the 7, and then we look in that corresponding row and column where they meet. That's 10-3. So 6 plus 7 is 10-3, or 13 if you insist. And many of the features of the earlier table that we were talking about are replicated here in this larger table. The pattern is really the same, it's just that everything gets extended. So along every row we're still increasing by 1. Along every column we're still increasing by 1 as we go down. Along these cross diagonals the values are still constant. And along this main diagonal we're going 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's the standard terminology. Simplified terminology: 2, 4, 6, 8, 10, 10, 2, 10, 4, 10, 6, 10, 8, 2, 10. There's another aspect of this that I want to point out, another important sort of cross diagonal, which is this one right here. Okay. So when students learn this table, of course it takes them quite a long time to learn it. This is not something to be done in a week. This takes months to learn for most young people. But this particular cross diagonal is, I think, very helpful. Here are the places where the two numbers add up to 10. So 1 plus 9 is 10, 2 plus 8, 3 plus 7, 4 plus 6, 5 plus 5, and then symmetrically 6 plus 4, 7 plus 3, 8 plus 2, and 9 plus 1. Those are the various combinations of two numbers that make 10. And those are kind of an anchor or sort of some fundamental points that I think add some structure to the table. So for example, if you want to know what 7 plus 4 is, if you remember that 7 plus 3 is one of those important combinations that makes 10, then 7 plus 4 will be one more, so it will be 10-1. While 7 plus 5 is two more, so it will be 10-2. So again, the same comments that I made about the earlier table apply to this one. I don't have any particular suggestions on how students have to learn this table, but learn it they must. And they must learn it in such a way that it becomes rote, that it becomes so ingrained that they know the answer immediately without having to pause and think. So although it's nice to have students thinking independently and making discoveries, it's also very important for young people to learn things by rote. If necessary, to repeat them over and over again until they learn them. At first, they should be aware of the reasons for any entry. They should know, or at least be able to compute and check for themselves that if you take 4 and 8, for example, then you do really get 12 or 10-2. They should be able to check that. But once they've checked it and are confident that it's correct, then they must memorize it. They must repeat it and see it in enough different situations so it becomes completely automatic. And that's very important. Students who are not able to do that are at a handicap with mathematics. So this is a place where rote learning is absolutely essential, and one way or the other, young students have to learn this table. There is no escaping it. It forms the basis of further additions and arithmetical competence later on. In our next video, we might talk a little bit more about aspects of addition, give some examples of addition in practice to try to solidify our understanding of the addition tables. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.